Alrighty, everyone, we just got it okay to start the final planetarium show of the day. So I want to put away our space trivia question, folks, because now we're heading into the unknown. And welcome everyone to the Morrison Planetarium. Really quickly, I just want to introduce myself. My name is Christian. I want to be your planetarium presenter. And just a heads up, located at the very tippy top of the planetarium, just behind you at the control booth. Hey, good afternoon, everybody. Good to see you. Don't hurt your necks, though. Look before you into the dome. Everything that you see in purple is going to be one really big screen, thanks to the help of 6 different projectors hidden throughout the dome. And if you're looking for our projector systems, folks, it's going to be located just below that purple glow all throughout the room. Now, I'm happy to have you here because you're in for a special treat. My favorite show to do here called Tour of the Universe. Now, just to give you a heads up, this show is completely live, so you're going to be hearing my voice for the next 30 minutes. And we're going to be starting off pretty close to the Earth, and we're going to be zooming all the way out, starting from Earth all the way to the edge of the observable universe. Hopefully, by the end of this show, you won't have an existential crisis of where we are in space. But just a heads up, we're pretty small in the grand scheme of things, so just a forewarning. And before we get started with the show, I got to go over some quick house rules just so that we're all on the same page and have a good time. First off, there's no food or drinks allowed in, so if you brought any snacks, make sure those are put away till the end of the show. Also, if you happen to have any cell phones, smartwatches, anything that makes bright white light, now's a good time to put those away as well. These can be very distracting. And if you need to leave early, the exits are going to be at the top of the planetarium, so always make your way up the stairs to exit. And if the staircase is a little bit too steep to climb, don't worry, just remain seated. Once the show's over, we'll have a staff member escort you to a lower exit when the show ends. So just stay seated for a bit longer. And last but not least, folks, this show is very immersive thanks to our 75-foot dome above us. If at any point during the show you start to feel overwhelmed, you start to experience motion sensitivity, there's a really quick and easy trick to ground yourself. All you have to do is close your eyes, take in a few big deep breaths, then your brain will remember that you're sitting in a planetarium in San Francisco and not hurtling across the universe, at least not more than the usual. But with that being said, it looks like we're ready to start our show, so I invite you to sit back, relax, gaze into the dome before you, because here comes Tour of the Universe. All right, everybody. As I mentioned, we're going to be starting off pretty close to the Earth. We can see the city lights just down below, but we're going to be starting off a little bit higher at this really amazing spacecraft right in front of us called the International Space Station, or the ISS. Now, a lot of people tend to ask me, hey, Christian, what is the ISS? I always hear about it in the news and articles, but I don't really know what it is. Well, folks, the International Space Station is a research facility. It's a laboratory that orbits around our planet. And they conduct many different types of science experiments up here. For example, some of the things that they tested out are what happens when you try to grow plants in space. Do the plants grow the same? Do they grow differently with less gravity? Which way do the roots grow? Another one is what happens when you try to spark a match in space? Does the flame act the same? Does that act differently? And one of my favorites is where they had two identical twins. One twin lived on Earth for about a year. The other one lived on the ISS for a year. After that year, they compared and contrasted the two twins. Turns out when you live in space for a long period of time, you tend to age a little bit slower. But not only that, you also lose a lot of muscle because you don't have as much gravity working down on you all the time. So if you plan to live in space for a long period of time, remember to exercise daily. And also, what's really incredible is that the International Space Station looks really big here in our dome, but it's not that big in actuality. It's only about the size of an American football field. If you've never been to an American football game, that's okay. You can also use the entire museum we're sitting in. That's roughly how large it is. Also, what's incredible is that the International Space Station is traveling at an incredible speed. It's traveling at a whopping 17,000 miles per hour, where it orbits once around the Earth every 90 minutes, and it experiences 16 sunrises and 16 sunsets a day. Whew, how romantic. Also, this looks really far away from our planet as well, but it's not too far either. The ISS is only about 250 miles above the surface of our world. 250 miles, that's like going from San Francisco to Santa Barbara, a nice little road trip to get away with the family for the weekend, so not too bad. But to tell you the truth, folks, this is as far as we put humans into outer space nowadays, only 250 miles above the surface of the world. The reason why is because traveling into space is very expensive. You got to build yourself a rocket ship, buy yourself one, or pay for a ride. And once you do that, you have to account for all the rocket fuel. You got to be able to escape the Earth's gravity. And once you acquire that, you have to account for all the food, water, all the air you're going to be breathing while you're up in space. So the bill gets quite costly quite rapidly. But, folks, the International Space Station is just the first stop on our tour of the universe. So now we're going to see it slowly fade away to the city lights down below. And before we lose track of the International Space Station, I want to add a nice little orbital path so we can see it as it slowly fades away. All right, everybody. Now we're able to see our entire planet Earth from this vantage point. And I want to let you know that the space program that I'm using here in the planetarium is something that you can go home and download if you want to fly through space, just like how I'm doing. The space program that we're using in here is called OpenSpace. So if you go to your favorite search engine, type in OpenSpaceProject.com, you can come across a link, you can download this, and it's a whole lot of fun. Just to let you know, OpenSpace uses a whole lot of processing power. So if you have an older computer, you may want to get something newer or something that has much more processing power, because this pulls real data from satellites that are constantly orbiting around the Earth. So it's a really fun program to use. But now that we have a sense of what we're using here in the planetarium, let's make our way over to our nearest natural neighbor to us in space, the moon. And folks, we humans have been to the moon before. That was between 1969 and 1972, thanks to NASA's 6 Apollo space missions that brought a total of 12 incredibly lucky guys to walk on the surface of the moon. And folks, that was the only brief presence of humans on another body in the solar system. So not too many folks. But again, last time we sent humans to the moon was 1972, a little more than 50 years ago or so. But don't worry, folks, we humans are making a return trip back to the moon in the next few years, thanks to NASA's new space mission in the works called Artemis. Pretty much with Artemis, NASA wants to send humans to Mars. But before we send humans deep into the solar system, we got to figure out exactly how we're going to be able to live out here in space. So the moon is the perfect stepping stone to figuring out the logistics of doing that. And what's really incredible is that they're going to be sending the first woman to the moon, but not only that, they're also going to be sending the first person of color to the moon. But not only that, they're also going to be setting up lunar bases throughout our moon. Pretty much our technology has greatly improved in the last 50 years, so we're able to conduct much more science in a much more compactable size. And one place that we definitely want to set up a lunar base is the south pole of the moon. The reason why is because we found ice there, and that's going to be very helpful because we can melt that ice, pass electricity through it, separate the hydrogen and the oxygen, and both of that stuff's really valuable when you're far away from home. So look out for any news about Artemis in the coming years. We humans should be heading to the moon relatively soon. And folks, sometimes when we look up at the moon here from Earth, it looks incredibly close. Feels like you can reach out your arms and touch it. But the moon's incredibly far away. It's about 240,000 miles away from planet Earth. 240,000 miles? Some of the adults in this room may have a car with that many miles on it. And if you take better care of your car than I do, you can even imagine driving to the moon if you drove for about 4 months nonstop, going about 80 miles per hour. Although we wouldn't recommend it, the roads out here are poorly maintained. Hee hee hee. And from here on now, folks, we're going to need to use a more useful measuring stick, because at this scale, using miles, that's kind of like using inches to describe the distances between cities, because space is so big. So astronomers use a more convenient measurement known as light speed. And light travels at a mind-boggling speed of 187,000 miles per second. That's roughly about 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so or since, well, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But at last, folks, it's time for us to leave the moon behind. So everybody say bye bye, moon. Aw, so cute. And now, folks, we're going to see the moon start to slowly fade away, just like how we saw earlier with the International Space Station. And just like before, I'm going to add some trails so we can keep track of some of this stuff in space, because again, space is incredibly large. So all these orbits that we're now seeing on screen, these are the orbits. Well, the first one's the moon's orbit, and then all the other ones, that's the planet's orbits. And folks, on our journey today, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to the help of computer models like OpenSpace, showing us the most accurate images and information available to us. And now, the nearest star to us, the sun, should be coming into view. So here comes the sun. Do. And also, folks, the sun is incredibly far away. It's about 93 million miles away from Earth. Whew, that's a good distance away. But in terms of speed of light, that's not too far. In order for light to travel that 93 million miles, it only takes light about 8.5 minutes at the speed of light. 8.5 minutes, that's really fast. And this is a really good concept to keep in mind, because even though that the sun and the earth are really far away, it takes light time to travel these huge distances. So when you hear people say, hey, look, we're looking at a star that's 70 light years away, well, you're looking at that star as it looked like 70 years ago, because the light that just reached us took 70 years to get all the way to us. So when you look at really far away objects in space, it's kind of like looking back in time in a sense, which is really cool. But now that we have a nice bird's eye view of our solar system, we're going to do a quick refresher of what we have. Right in the middle of our solar system, we have our star, the sun, the biggest thing by far. The closest planet to the sun, we have Mercury. Then we have Venus, and then Earth. And of course, we have the famous red rocky planet, Mars. Now, these are the rocky terrestrial planets. These are places where we can actually land a spacecraft on. And then past the orbit of Mars, we have the main asteroid belts. And this is where you can find roughly about 1 million asteroids in this region. Whew, there's a lot of rocks out here. And then past the asteroid belt, you have the really big planets, the gas giants, the Jovians. We have Jupiter, the largest of them all. Saturn, famous for its rings. And then we have our icy gas giants. We got Uranus, the funny one, and Neptune. And of course, we can add everyone's favorite and lovable dwarf planet, Pluto. So here comes the orbit of Pluto on screen, just down below. Now, a lot of people don't realize that Pluto hangs out here in this outer part of our solar system called the Kuiper Belt. And you're probably wondering, what's the Kuiper Belt? I've never heard of that before. Well, folks, this is the Kuiper Belt. So the Kuiper Belt is like a second asteroid belt. What you're mostly going to find are icy asteroids and short period comets that don't stray too far away from the sun. And this is located beyond the orbit of Neptune. And what's really amazing is that we came across a lot of these objects back in the year 2006 because our telescopes and technology greatly improved. We're able to see much smaller objects much further away. And in 2006, we came across more than 400 objects out here in the Kuiper Belt region. Some of this stuff was bigger than Pluto. We couldn't call all these things planets. There was just way too many of them. So all the astronomers on planet Earth had a great big meeting. They had to figure out what exactly you need to be considered a planet. Well, they came up with 3 different criteria, and folks, that was the day in 2006 that Pluto went from being a planet to a dwarf planet. And I know a lot of people still have hard feelings about it. I still kind of do. But that's the really cool thing about science, because as our technology improves, we're able to make better assessments, and science is constantly updating and changing, and I just love that. But for now, I'm going to be putting away the Kuiper Belt region because that's just a whole lot to look at. And now, folks, I'm going to be adding on screen some of the many different spacecrafts we sent out in the 1970s to explore our solar system. There we go. Now on screen we have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2, and the latest of them all, New Horizons, which did a quick flyby of Pluto in 2015. You can see that interaction down below. Now, all of these spacecrafts are all traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventures, Voyager 1, has not traveled as far as light travels in a single day. In order for sunlight to travel all the way out to the orbit of Pluto, it takes sunlight about 5 hours at the speed of light. 5 hours to get all the way out here. Not too bad. But now, folks, it's time for us to leave our planetary scale behind us because now we're going to be heading out into interstellar space, the space between the stars. Distance now becomes so immense, it's going to take us about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And it looks like Alpha Centauri just passed us on the top right-hand side. You can see a star that's moving pretty close. So again, we're right in the center on the screen here. Alpha Centauri is going to be on the very top right. And again, 4 years at the speed of light just to reach the next star system to us, folks. But that doesn't really put into perspective how long it would take us to travel that distance. Well, if you're getting a rocket ship today, made your way over to Alpha Centauri, it's going to take you roughly about 8,500 years to make that trip. Whew. But let's stop consider whether humanity has made its presence known beyond our solar system, because now, folks, we're going to be stepping inside something known as the radiosphere. And again, we're now inside something called the radiosphere. And this represents the current limits of the most distant radio signals humanity has ever broadcasted, or rather leaked into outer space. And this all extends about 90 light years in all directions out from the Earth. And this first began in the early 1930s with strong radio waves, early television, radar signals, and then later, the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before that. But the earliest radio was not quite powerful enough to escape the Earth. And since all these signals are electromagnetic, they're traveling at the speed of light. So this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is constantly expanding at the rate of 1 light year per year. So is anybody out there listening? And folks, I'm going to be adding these many markers onto the screen. These markers indicate many thousands of stars astronomers have discovered over the last 30 years, which has at least one or more planets orbiting around them. We call these planets exoplanets, and we're looking for any of them that are Earth-like with conditions suitable for life as we know it. So far today, we found more than 5,000 confirmed exoplanets in the nearby vicinity to us, 5,000 other worlds besides our own. And that number is going to be increasing as the years continue because we have space telescopes where their whole purpose is to find as many exoplanets as possible. Now, to say if any of them are Earth like with conditions suitable for life as we know it, well, we cannot answer that question quite yet. Pretty much new space telescopes are being developed, so those are on the drawing boards. They got to get built and then they get launched into space. So we've got a little while before we can answer that question. But the more important point here is that quite a few of these planetary systems are within that 90 light year limit of our radiosphere, and they could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in and answer back, well, the communication delays between hellos, they could be decades in time. And of course, folks, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. And for now, folks, I'm going to be putting away our exoplanet markers away, but I'm going to leave our radiosphere up on screen. As huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way galaxy. All right, folks, we're now looking down on our Milky Way galaxy, and I gotta ask, can anybody see their house from here? Just kidding. And folks, our Milky Way galaxy is incredibly large. If you wanted to cross it from one side to the other, it's going to take you about 130,000 years to cross the Milky Way. It is really big. And folks, our Milky Way is so incredibly huge, we estimate that there's at least 300 billion stars in the galaxy. If our recent discovery of so many exoplanets just within our small neighborhood, within this vast, big star city is any indication, well, there could possibly be potentially be billions of planets and potentially millions of Earth-like planets throughout our single galaxy. And before we leave the Milky Way, I want to show you what it looks like from the side. If we spin all the way down, you're going to notice that the Milky Way kind of looks like a big flat pancake in space or a frisbee. And this is important to think about because when astronomers and scientists want to learn about the universe, it's much more easier for them to point their telescopes galactically north and galactically south, instead of looking to the plane of the Milky Way, which has planets, stars, debris, nebula, things that block their view of the universe. So keep that in mind. We like to point our telescopes galactically north and south. It's much easier to see things. But folks, the Milky Way galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So in this giant leap, every single point of light that you're now going to see no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. And we live in a local galaxy group, which contains about 30 galaxies, large and small. Also includes the nearest large spiral to us, the Andromeda Galaxy, only 2 million light years away, just next door, and heading right for us. We're going to get to know it pretty intimately in about 5 billion years, so mark your calendars. And as we continue expanding out, folks, you're now going to realize that galaxies are not evenly distributed throughout space, where there's one galaxy here in a nice little neat line and another one here. Instead, galaxies like to clump together in large groups and clusters. Or they like to create voids where there's very few galaxies or no galaxies at all. So we can see some nice galaxy clustering towards the center of our screen over here, also off to the left-hand side. We can also see some voids on the very top left of our screen. So you can kind of think of galaxies like people. They like to hang out together or they like to avoid each other. And folks, this picture that we're now looking at represents the closest 30,000 galaxies to us in a space over 300 million light years across. We got to give thanks to an amazing researcher by the name of Dr. Brent Tolley, who compiled this amazing representation over decades of time with the help of dozens of astronomers working aside him. So big shout out to Dr. Brent Tolley. I love flying through this galactic map. But now, folks, we have automated systems that are mapping even the most distant galaxies. So now we're about to see the large-scale structure of the universe. And remember, every single point of light that you're seeing is not a star, that's an individual galaxy. And as we start to spin around, folks, you're going to notice that the large-scale structure of the universe is not in the shape of a bow tie or a butterfly. Remember when I mentioned that we live in a big flat spiral disk of the Milky Way galaxy? Well, if we were to line up the Milky Way, it's going to line up just like so, right down the middle, vertically like so. And again, we like to point our telescopes galactically north to the left and galactically south to the right-hand side. But astronomers still want to make sure that there was galaxies through the plane of the Milky Way, so we have this purple survey of galaxies right in the center. You notice they were still able to find them, just not as many and not as far. Pretty much we have to wait for our technology to improve, and once that happens, we'll be able to fill out all these areas that haven't been filled in yet, so it's just a matter of time. Ooh, and speaking of time, we're almost out of time. So let's continue pressing on, because now we're going to be encountering these really distant, far-away objects known as the quasars. And folks, the quasars are represented by orange dots on either side of the large-scale structure of the universe. And quasars are short for quasi-stellar radio sources. These blazing objects are all billions of light years away. So now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe. And before there was a teenager, there was a baby. So let's press back to a time before quasars, before planets, stars, and even galaxies began to form. Folks, we're about to see the very large scale structure of we're about to see the very edge of the observable universe. And here we are, folks. What we're looking at is something known as the cosmic microwave background image, or the CMB image for short. And all evidence indicates that the universe that we live in is about 13.8 billion years old. This is data compiled by Planck and other radio telescopes. And this is a very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And this is not your typical photo either. Instead, this is a temperature density image, with the light echoes of the Big Bang are color coded, with the lighter areas corresponding to the hottest, least dense regions, and the dark areas the coolest, densest regions. These fluctuations in temperature and density are extremely tiny. They vary no more than 1 part per 100,000. But these tiny differences eventually gave rise to that large scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Folks, though our view here is of the outer edge of the known universe, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But folks, we've traveled as far back as the law of physics can physically allow us to go, so we only have one direction left to go, back home towards planet Earth. So let's find a nice entry point through all these quasars and galaxies, and let's make our final trip back to planet Earth. All right, everyone, we're crossing an expanse of over 13 billion light years. We present you with this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. We live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reaches of our eyes, preparing for the eventual race between the advancement of technology and the accelerating expansion of the universe. And with that thought, everyone, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope, and there's astronomy clubs all around the world that invite people just like you to look to their telescopes and peer into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But it looks like we just made our way back into that radiosphere, and we're heading straight for our solar system, our star system, in the vastness of space and time. And now, folks, we're about to pass those spacecrafts we sent out in the 1970s to explore our solar system, passing the orbit of Pluto in the Kuiper Belt region. Now we're making our way to the third rock from the sun, our homeworld, planet Earth. All the people that we know, loved, ever heard about in history all lived on this one planet. And now we're about to pass the orbit of the moon, the furthest we've ever sent humans out into outer space. And as we make our final approach back to planet Earth, folks, this is going to be the end of our Tour of the Universe show. And I want to thank y'all so much for stopping by and watching it with me today. I hope you did enjoy it. But hey, look at that. We're back home safe and sound just in time for dinner time. And that's all the time that we have for today. So thanks for stopping by, and I hope you get home safely. We'll see you next time, everyone.